Assalamualaikum and very good day. My name is Abdullah Muqri Bin Rasdin and my partner is Lok Yen Pun. For my major presentation today, I will be presenting on erosion and sedimentation control. The lecturer in charge of this part is Dr. Tamizi Ismail. So in this video, I will be touching on introduction, site analysis, soil loss estimation, sediment yield, sediment basin and temporary drainage. The content of my presentation is the introduction, site analysis, rainfall estimation, temporary earth drainage, sediment control, sediment basin, erosion control and conclusion. So for introduction, Malaysia has a lot of different kind of building project and all of them are at risk of erosion and sedimentation if they are not done right. Due to a lot of siltation and control, soil erosion and sedimentation in the construction area will definitely pollute water and hurt the quality of water in number of water courses and receiving waters. So the water flowing out of the construction area doesn't pollute the water, the eroded soil and the sediment loss will need to be dumped and treated in one place. Soil erosion happens when raindrop hit the soil or when water move over the soil and causes shear. This causes soil particle to break off, get cut off and move. The sedimentation is the process by which sediment that has been moved by erosion and dumped elsewhere on the land in the lake stream build up. The SCP brings up several problems with the environment such as soil erosion and water pollution. Now we move on to the site analysis. This project site is located 1.3 km northwest of SMK Puteri Wangsa and 1.2 km southwest of SMK Puteri Wangsa and 1.3 km southeast of Stesen Penguatkuasa JPJ Ulu Tiram Johor, which is Mukim Tebau. For the design purpose, we have divided the catchment area into three, which is A, B and C. And the total area of development is 451,009.01 meter square and the highest level of the proposed level is 88.99 meter and the lowest level is 31.17 meter that we receive. The legend is for our reference only. Next is the runoff management BMPs. For the erosion and sedimentation control plan to work, it is important to take care of the stormwater runoff in the right way. BMPs for the runoff management are the temporary structures that are set up at construction site to prevent erosion of the channel. Downstream of the construction site, there will be too much sediment. The way the BMPs are made will make sure that the runoff from the construction site doesn't hurt the water resources too much. Most of the time, the amount of the rain that fall make BMPs for managing runoff more important. Using a temporary earth drain or the construction site is one way to manage the runoff. The temporary earth drain is used to deal with the stormwater runoff and the side of the drain is made to get the best flow and reduce the risk of soil erosion and sedimentation. The purpose of this drainage control is to stop gully erosion risk from happening as well to control the flow. Next, we move to our first approach to project design, which is rainfall estimation. The rainfall estimation is involved of frequency, duration and intensity analysis of rainfall data. The parameters that need to be considered are first is the average recurrent interval ARI. ARI is an estimate of the amount of rain and water flow based on the frequency or return period chosen. ARI is the average amount of time between rain events that are bigger, last longer or have the same amount of the rain. The first stages of the building are expected to be finished in 2 years, so the minimum ARI of 2 years is enough. Next, we have a time concentration TC. Is the travel time of runoff flows from the most hydraulic remote point upstream in the contribution catchment area to the point under consideration downstream. In the design, of stormwater drainage system TC is the sum of overland flow time T0 and the time of travel in drainage TD. In early stages of construction, the site is considered as natural catchment area due to no development beginning. Therefore, the time of concentration including the travel time in natural channel for natural catchment area is expressed as TC is the time concentration in minute, T0 is the overland sheet flow travel time, TD is the drain flow travel time, L is the length of overland sheet flow, and N is the Horton roundness value, S is the slope overland surface, small l is the length of drainage flow, V is the velocity of the flow. Next, the average rainfall intensity. Intensity, duration, frequency, which is IDF curve, show the relationship between the design rainfall data required for the use of peak flow estimation. Average rainfall intensity can be estimated by using empirical equation, which is I equal to lambda T times K over D plus theta times N, where I is the average rainfall intensity, T is the average recurrent interval ARI, D is the storm duration hours, lambda K theta N is the fitting constant dependent on the rain gauge location. Next, we move to the peak discharge flow estimation. The building site has been separated into several minor catchment zones to maximize peak outflow. Several methods are available for determining peak discharge QP. The rational method for small catchment only, and the time area method are suggested for peak discharge estimation in Malaysia. This construction site has been divided into 3 parts and every catchment area also been divided into sub-catchment area for every drainage. We use the equation to calculate peak flow, which is Q equal to CIA over 360, where the Q is the peak flow, C is the runoff coefficient, I is the average rainfall intensity, and A is the drainage area. These are the results that we get after we analyze it to 3 parts of each catchment area. So the calculation of rainfall estimation, we take the catchment area A as our example. Then according to the table in 2.2 in MASMA, we need to find the T0 and the equation of the T0 is 107 N times L power of 1 over 3 over S power of 1 over 5. So we need to find the value of length and S slope, which is we need to find based on our plan layout. So this slope we find from our plan layout, and then the length of the temporary drainage also is from our plan layout. So we substitute the value into the T0 equation, and then we get the T0 is 8.298 minutes. Then for the velocity is, for the site visit, the depth of channel is assumed at 0.3 meter and the width at 0.5 meter. Then we use the formula, we get A is 0.285 meter square, P is 1.5817 meter, R is 0.1802 meter. Then we substitute the value into V equation, then we get the value of V is 3.791 meter per second. Then we substitute the value of V into the TD equation, then we got the TD value of 0.57 minute, and then we can find the value of TC by addition of the TD and T0. Then we get the TC at 8.88 minutes. To find the average rainfall intensity I, according to the IDF constant in MASMA, pusat perkananas has the following fitting constant, which is lambda is equal to 54.265, K is 0.179, theta is equal to 0.1, and N is equal to 0.756. So the ARI location is in Ulutiva, and the waiting period is 2 years as we mentioned before. And you use the equation I equal to lambda T power of K over D plus theta over N, and then we substitute the value, we got 176.386 mm per hour. Then we calculate the value of Q peak discharge estimation, Q equal to CIA over 360. We substitute the value and we got 0.57 meter cube per second. So these are the result of average rainfall intensity that we calculate using the same method for catchment area B and C, and we got the Q peak of the flow. Next, we're moving on to temporary drainage. The design of temporary drainage for our project is used to the trapezoidal shape open channel. As a reference, we assume the trapezoidal shape open channel is able to cater to the flow of the water. However, we adjust the dimension to be suitable for construction. Is it able to cater the larger water flow compared to the rectangular and triangular shape channel? So we use the trapezoidal section with the side slope of 1.5:1, and we use the formula Q equal to A R power of 2 over 3 times with square root of S the slope over N. And A is the area we can calculate by by plus zy square. Thus the z is 1.5 as we use. So we use the Manning formula where the Q is the flow rate of discharge, A is the cross section area, R is hydraulic radius, S0 is the channel bed slope, N is the Manning coefficient of channel roughness, shape of the drain is the trapezoidal. To design cater the peak discharge, we take the drainage one as our example. So the S0 is the slope we get from the plan layout, and the N is the constant. So using the Manning equation, first we need to find the R value. So first we use the T equal to B plus 2ZY to find the value of T. Then we substitute into the A formula, then we get the value of A. Then we substitute into P formula, and then we get the P value. Of course, we can find the R value after we get the value of A and P. So the R value is 0.44 over 1.9422. Then we get the Q peak is 0.57 meter cube over per second. Then we use the formula Q capacity AV, and we times the value, we get 1.943 meter cube per second. We know that Q peak capacity is bigger than Q peak, then therefore it's okay. The freeboard we use is 0.3 meter for the trapezoidal section. These are the result of temporary drainage. We use the same method of calculation using the Manning equation to find the Q capacity for every zone for A and B and C. So we can see here the Q peak is lower than the Q capacity, therefore it is okay. At the beside, we can see these are the example of long section of temporary drainage to prove that the connection of sediment basin and purpose is connected, so it does not below the sediment basin level. Next is the sediment contour BMPs. So the construction pollution is most common. Sediment are the most common contaminant in waterways. This form of pollution can harm aquatic insect, fish and other species. Common construction operation that cause erosion and silt generation should include the sediment contour BMP. Sediment contour is a practice or facility that prevent eroded soil from polluting surrounding waterways. The structure is frequently situated downstream of the building site to trap extra sediment. This structure should be well designed to meet the site needs. Then we have the soil loss estimation. Soil loss estimation is a set of specialized management strategies which help to enhance the prevention of the soil being eroded from overuse, salination, acidification and other soil contamination. The most widely used formula for soil erosion is Universal Soil Erosion Equation, which is USLE. Consider the factor as the formula of A equal to RKLSCP, where the A is average annual soil erosion loss, R is a rainfall erosivity factor, K is the soil erodibility factor, LS is the topography factor that represents the slope length and the slope thickness, C is the cover management factor, P is the support practice factor. The summary of soil texture is the rainfall elasticity R factor soil loss for the catchment area A location in Ulu Tiram, and the R value in range is 40,000 to 15,000, and for evaluation purpose we choose the value R is equal to 14,000, and the soil durability K factor based on the location of the site, and our site is we use the Ulu Tiram series. So the designated catchment area A, B and C, we use the structure code, we got 2 and the permeability is 2, and we can find the K factor which is 0.035, and for A and for B is 0.39, and for C is 0.037. Next is the LS factor. LS factor is the horizontal slope length in meter and the slope thickness in percent. Need to be determined through elevation information available on site. For the three conditions which are existing earthwork, uncontrolled and earthwork control, the contour from the topographic map. For the disturbed condition, the design platform level can be used in order to evaluate average losses, the average slope and the slope thickness of the entire zone are referred. We refer the LS table to get the slope thickness and the slope length, and if we cannot find the value, we will use the formula to get the LS factor. The LS formula is LS equal to lambda 23.13 times Vm in bracket 0.065 plus 0.046 S plus 0.0065 S square. So the example calculation for the existing slope, when we take the catchment area A as our example, the horizontal slope length is the horizontal slope that we get from the plan layout, and then the slope thickness if we use the highest level and the lowest level of the slope, and then we get 10.395%. Then we substitute the value into the LS formula, and then we get 4.571, and we use the same method and calculation for the catchment area B and catchment area C. So for the earthwork, uncontrolled and controlled, we use the same method and the formula is also the same. Just the difference is we use the design platform level as our elevation, and the difference between it we will be applied, and we get the different error factor with the existing one, but our controlled and uncontrolled still remain the same. So for the determination of C factor, for undisturbed condition, the entire site is covered 95% forest coverage, and the C factor is 0.03, and for the earthwork uncontrolled, C factor is 1. For earthwork control, C factor is 0.05. So determination of CP factor, for the existing condition, no management support practice is provided, which is the undisturbed site, and also for the earthwork uncontrolled, therefore the P factor is 1.0, and for the earthwork control, P factor is 0.5. The determination of soil loss, we use the same formula. The estimation of soil loss catchment area can be determined using the formula of R times K times LS times CP. And then we substitute the value, we get the value of 65.114 ton HR per year. So these are the result of the existing earthwork uncontrolled and earthwork control. We get the value for the parameter for each catchment area B, A, B and C. Next, we moving on to the sediment yield estimation. Sediment yield is the amount of the sediment expected at the end of the drainage point from the designated site. Therefore, this estimation is used to predict the amount of sediment for sizing and maintenance of sediment control BMPs. The modified universal soil loss equation MUSE is the normally used in the estimation of sediment yield of a catchment as a result of a specific storm event. The estimated amount of the sediment storage volume is used to the sediment basin or trap design. The empirical relationship for individual storm event is expressed as Y equal to 89.6 times with VQP times with 0.56 KLSCP, where the Y is the sediment yield per storm event, D is the runoff volume, QP is the peak discharge, KLSCP is the USLE factor that we used before, and we get the value of A, B and C for the catchment area. So for the example of the calculation sediment yield estimation is first we design the storm. The design storm we use the formula rainfall intensity times with storm duration. So the design storm we get is 30 mm, and the catchment area is 11.24 HA, and the time concentration is 11.452, and the intensity design storm is 156.261 mm as we calculate before. And we calculate the peak discharge. We use the rational method. One of coefficient C we use is 0.5, and the rainfall intensity we use the I is 156.261 as we use as the same before. Then we calculate the runoff volume using the rational method hydrograph method, which is the type 2. We use the value of TC. We substitute the value into the QP CIA over 360. Then we get 2.439 meters cube per second. Then we substitute into the V formula, and then we get the V value, which is 1675.886 meter per second. Then we calculate the calculation of sediment yield using the formula we mentioned before, Y equal to 89.6 times with VQP times with power of 0.56 times with KLSCP. Then we get the value of the sediment yield is 310.776 ton. So these are the result of sediment yield estimation for all of the basin A, B and C. We use the same calculation and method before to find the value of all the parameters. Then we moving on to the sediment basin design. The sediment basin is one of the sediment control BMPs that is used to collect the storm water and runoff from the disturbed area at the construction site to store and retain the sediment and another large particle from being discharged out of the construction site. The protection structure against erosion and detention basin is constructed, which is known as the sediment basin. A sediment basin typically consists of a dam, an emergency spillway, a riser pipe outlet, and impediment, which is function the same way as the same sediment trap but cater to a larger catchment area. So for the step for the sediment basin design, first we use the catchment area as our first example, and from the soil desiccation, dry sediment basin is chosen for the catchment area A, as the soil texture is classed is sandy loam. And for the basin dimension, we use the same value as we calculate before, but required surface we get 200 meter square, and required total volume is 240 meter cube, and the catchment area is the same 11.24 HA, and we substitute the value into the formula of A, and we get 2248 meter square, and the total basin volume required B is equal to 2697.6 meter cube. For the settling zone, the required settling zone is we use V I, we times the half of the total volume, we get the volume is 1348.8 meter cube. Then we select the settling zone depth Y equal to 0.6 meter. Then we try the settling zone average, we want equal to 35.0 meter, and then the settling zone average we use the formula L1 equal to V1 over Y1 times W1. Then we get the value of L1 is 75 meter, and the average surface area is 35 times 75, we get 2625 meter square. Then we check in the settlement zone dimension, we use the ratio method, and we get 125 meter, which is okay. And we do also for the L1 over W1 ratio, we get 2.14 meter, which is less than 200, and it's okay. Next is the sediment storage zone. The required sediment storage zone is as we calculate before, we get 1348.8 meter cube. So for the side slope, we use 2:1, and the dimension of the top sediment storage zone are, we use the formula W2 equal to W1 minus 2 times with D1 over 2 times Z. Then we get 33.8 meter. We also use for the L2, we need to find the length, and we get 73.8 meter, and we substitute the value into the formula to find the new V2, and we get the value of Y is with 0.57 meter. We use this for the value either one, and then we substitute into formula, we get the new V2 is 1420.056 meter cube, and it is larger than the old V2, therefore is okay. So for the overall basin dimension, at the top of water and the base, we calculate using the formula, and we get the value of 33.8 meter, 73.8 meter, 31.4 meter, and 71.4 meter. And the depth settling zone, we use that 0.6 meter. The sediment storage Y2 is 0.2 meter also. We use the side slope of 2:1. And the sizing of basin outlet with the spillway for this sediment basin must be designed 10 years ARI. Its proposed spillway dimension is 1.5 meter wide times with 1.2 meter height. The spillway level must be a minimum of 300 mm above the basin top level. To simplify the calculation, the following assumptions are made. So we assume the riser pipe flow is orifice flow to the top of the pipe only. Riser pipe head is 1200 mm. The height between the top and pipe and the spillway crest level, and the Q required is Q10, which is the Q riser. So the determination for the Q10 or the Q riser, we use this parameter, we set up, and then use the formula I equal to lambda TK over D plus theta N, which use the I4 intensity. So we get the value of 208.415 mm per hour. We use the rational method, we use the same coefficient 1 of C equal to 0.5. Catchment area A is the same, and then we substitute the value of CIA. We get the Q10 or the Q riser is 3.25 meter cube per second. So determination for the Q riser, we try with one orifice with diameter of 0.7 at the same level, and the allow head of 1.2 meter for the center of the orifice, and then we substitute the value into the formula of the Q riser, and then we get 1.12 meter cube per second. Last but not least, we need to sizing of the spillway. We try the dimension of B equal to 1.5 meter, HP equal to 1.2, and CSP is 1.49 from the table that we use, and the Q required we get is 2.134, and the spillway formula we use CSP BHP power of 1.5. We substitute the value, we get 2.938 meter per cube per second. Thus the total basin there including the spillway is 2.7 meter. We need to sum out all the Y1, Y2, HP and freeboard, and then the value is larger than 2.34 meter cube per second as we calculate before, therefore it's okay. Then we need to find the trapping efficiency after we calculate all the calculation, and the sediment yield as mentioned is 310.776 ton, and the efficiency is 90%. Total sediment yield trap is 279.698 tons. We need to convert to soil bulk, which is 1818 meter cube, and the volume designed for the sediment storage zone is 1420.056 meter cube. Hence, provided the sediment basin is capable to occupy the sediment as is large than 153.849 meter. So these are the results of sediment basin design. We use the same method and calculation as I mentioned before to find this sediment basin for 1, 2, 3, and we get all of the parameters here, and these are adequate all the design. So these are the sizing of the basic outlet and tapping design efficiency. The plan wheel and the section wheel and downstream elevation has been drawn for the sediment basin, and all dimension is displayed on the drawing. So next we move to the erosion control BMPs. So we have first one is the silt ferns. A silt fern is a porous closed temporary sediment barrier used to collect the silt and sediment during the construction, and is affordable and easy to remove because it's supported by the wooden and metal pillars. This device not filter runoff, but it retains sediment from disturbed regions to prevent from the entering stream and reduce runoff velocity. And our present places silt fern also temporary drainage and the stockpile. Silt fern are utilized during earthwork until revegetation and permanent soil stabilization can occur. So this plan costs less than losing aquatic habitat, digging and sewage channel, and removing the silt from the municipal storm drains. Silt fern should be inspected and maintained regularly, especially after each rainfall. If the fence is torn and has a gaps, it should be replaced properly. When the sediment reaches half or 2/3 of the fence height, it should be removed and disposed of. Now we have the wash tools. So the dust from the land removal and vehicle movement will harm air and water quality, as we know in our world right now. All of which should be dust free, and wash tools are one of the approach to prevent the dust during the construction. And wash tool also is situated at the stabilized construction exit point to remove the silt from the tires, undercarriages and machinery. And any construction machinery must be washed at the wash tool. Mud and soil are removed. This keeps construction dirt off municipal roads. Runoff from the wash tool must be channeled to the sediment basin. To preserve the wash wets effectively and efficiently, the sediment must be removed frequently. A drainage ditch must be transport wash area runoff to sediment basin. To preserve the wash wets effectiveness and efficiency, the sediment must be removed frequently. Next, we have the seeding and planting. Soil is stabilized over time by seeding grass and planting trees, bushes and ground covering, and is appropriate for use both during and after construction in any graded or clear areas where construction activities have finished, including to the open space, cut and free sites, steep slopes, spoiled stockpiles, vegetated swales, landscape corridors and stream banks, and it's the most appropriate and cost-effective covering for any damage or bad soil. Last but not least, a stockpile. A stockpile is a pile or storage facility for bulk goods, ports, refineries and manufacturing facilities use the stockpile. Stakers create the stockpile. Reclaimer recover materials. Refineries, port and mine usually have the stockyards. Coal is dumped from the dump truck, bulldozer or conveyor booms to construct a simple stockpile. Stakers construct stack along conveyor, and reclaimer retrieve a coal for product loading, and the construction site has 3 stockpile. To end my presentation by the conclusion, the AICCP department has carried out the thorough analysis and created in it according with the standard outline in the MASMA second edition along with the appropriate presumption. Generally speaking, this project provides the design of trapezoidal shaped channel for the temporary soil drainage, and we are able to break wet sediment effectively to accept the settled sediment by performing soil loss and sediment yield estimation. Therefore, the design we created is appropriate for the controlling erosion and sedimentation to ensure that the construction progress is safe and able to avoid the detrimental effect to the environment. That's all for me. Thank you.